create in our proof. Then some more formal parts. We have this idea of proof versus proof of knowledge. The proof of knowledge is stronger than it's not just saying that there exists some secret. It is also saying that I know this secret that exists, that solves or that satisfies whatever equation we're looking at. And then the argument versus proof, this is really about looking at the computation power that the prover and the verifiers have, and to show that this will still hold true against a malicious prover or a malicious verifier. The process from the user point of view, if you're creating one of these, is, and for example, if you're using the projects such as Socrates on the Ethereum blockchain to create a zero-knowledge proof, you would first of all write your algorithm that defines what your proof is about, and this would be shared between the prover and the verifier, and then turn into a mathematical representation, as we've seen. This stage is going through, and this in terms of the Socrates project, what this gives out are two keys, a proving key and a verifying key. And this first stage is what's called the trusted setup. So there's a setup stage which produces our keys. The proving key is given to Peggy, and she can add her secret in and use her secret with this proving key to produce a proof. And the verifying key is given to Victor, and he can then use that to verify the proof that Peggy gives to him. More formally, these are some definitions of what it's about. I just want to show this to emphasize this secret parameter lambda. So in the zero-knowledge, and if you're doing a ZK SNARK, we generally have a trusted setup. Although, as we shall see, Mina doesn't have this, and this is a great advantage. But usually there is this stage called a trusted setup, and this is because to create our keys, we have to use a secret parameter, lambda, in this setup. And the problem with this setup is that if someone was to obtain lambda, gain knowledge of what that was, then they could use that to create false proofs. And they could create a proof that would evaluate to true even if they did not know the correct secret, if they didn't know the correct witness. So when we do this trusted setup step, we have to be sure that we do not leak this information. And in fact, this has been nicknamed toxic waste. And projects that produce zero-knowledge proofs or depend on zero-knowledge proofs may have quite elaborate ceremonies to get rid of this toxic waste and to do this this setup. Just to mention a couple, Zcash have done this ceremony a couple of times, and the first one had just a handful of people. The second one had a few hundred people, I think. We were recently involved, or about a year ago, we were involved with one with the Aztec project, which was held over a couple of weeks and involved a few hundred people doing a shared computation. And the point of this computation was that if just one person is honest in this setup process, in this ceremony, then the whole process succeeds. Or to look at it the other way around, it would require the collusion of every single person within the ceremony for them to share and work out this secret parameter lambda and to be able to cheat and make false proofs. So as long as one person is honest within the setup, then the whole process works. And in the Aztec setup, the Aztec ceremony, the first person to do this was Vitalik Buterin, the inventor of Ethereum, who I think is quite well respected and probably quite well trusted. So I thought we could have perhaps stopped at that point and all just trusted that he is honest, but we didn't. We all went ahead and had a few hundred people doing this setup, and it went ahead and succeeded. And Aztec is now a very successful project on Ethereum. This process of trusted setup is problematic, perhaps. In some ways, it's nice because you have some community participation in your project, but it is cumbersome. It does require resources, a lot of effort. So people have been trying to streamline it to some extent, and there have been different versions of ZK SNARKs, and these are some of the recent ones. Sonic, for example, and Plonk. Plonk is the one that is used by Aztec, and they have improved it by allowing this trusted setup to be reused under certain circumstances, so making the process a little bit more flexible, a bit more feasible. If we go through, look at some other types of zero-knowledge proof systems, I'll just show a couple here. We have STARKs and bulletproofs. Really, I just want to compare STARKs, I think. So STARKs are a very different way of doing zero-knowledge proofs, very different than SNARKs, and the very different technique to the one I described, and they have different features. So SNARKs are kind of a general purpose, kind of middle of the road, very useful. They have a nice small proof. You can compute the proof in quite a reasonable time. We have here some of the figures for these. STARKs, on the other hand, perhaps not quite as efficient. They have larger proofs, but they have other advantages. So STARKs, for example, do not require this trusted setup. They just need the prover and the verifier to agree on a hashing algorithm, and which is collision resistant. But once that is done, that's all that needs to be done. They're also quantum resistant. So if quantum computers become more feasible, this will attack some of the basic assumptions that underlie SNARKs. But STARKs will be fine for that. Bulletproofs also, they're kind of in the middle ground, I guess. They're not quantum resistant. They also rely on certain assumptions, but they don't require a trusted setup. So this idea of the trusted setup has really been getting rid of that, or making that more amenable. Has been a driving force in this area. But let's turn to how zero-knowledge proofs are being used, and particularly in regard to blockchains. So proofs can be used maybe in two main ways. There is a privacy aspect, so you may want to prove perhaps that you are above a certain age, so you could prove that you're above 18, but you could use the privacy aspect of a zero-knowledge proof so that the person accepting the proof would not know your exact age. But an area that we're more interested in is that it allows us to prove that a computation has been done correctly. And more so, it allows this, it's quite astonishing in the power that this has, and that we can do an extremely complex and time-consuming computation, and then use a zero-knowledge proof to prove that it's been done correctly. And this proof can be computed in very short time, and can be a very small size. So they really are a great way of compressing a massive computation down into something quite succinct, but that still is able to prove that that computation has been done correctly. So they've been used to solve some of the blockchain scalability problems. So they can prove, as we shall see, they can prove transactions are correct blockchain transactions are correct. For example, in the Ethereum projects that use rollups, they may use one zero-knowledge proof to prove that a bunch of transactions are all correct, and then post that proof onto the main chain, so that you don't have to look at all of the individual transactions. You will know that they're correct because you see the zero-knowledge proof. Okay, so that's our very quick introduction to zero-knowledge proofs, probably much too fast. Okay, yeah, does anybody have any questions? If you want to put them in chat, I'll perhaps answer a few at this stage, and then we'll go on to looking at Mina in more detail. As I say, it was a very quick introduction to zero-knowledge there, but there are some links that you can look at to give you more details. Okay, I'll keep going then. So we'll turn to the Mina project. So we know that blockchains have certain problems. They have scalability problems, And these can be not just in terms of the throughput of transactions, but in the size of the blockchain. So some figures here from April 2020. For an Ethereum archive node, you would need to have enough space to store 4 terabytes of data. So an archive node in this sense is one that keeps all of the transactions. So if you wanted to go through, verify all the transactions yourself, you would need to have you would end up with 4 terabytes of data on Ethereum. Bitcoin is slightly smaller, even though it's been running longer, but it's still a considerable size. And both of these blockchains are increasing in size considerably. And the reason we would want to do this is because we want to verify that the blockchain is correct. We want to verify the state of the blockchain. And this is one of the main reasons that we use blockchains in the first place, is that the idea that every participant in the system has the ability to verify the current state of the blockchain and can choose whether to accept or reject transactions and blocks. But if we get to the point where this is not really feasible for ordinary users of the blockchain, then we are to some extent losing some of the decentralization that we had. We're relying perhaps on archive nodes or other people to do this verification for us, and we will just accept that they have done this correctly. Maybe we don't, if we are running something on a phone, for example, maybe we can't really verify all of the blockchain ourselves as much as we would like to. So we are losing out to some extent because of the size of the blockchain. And this really is one of the main driving forces behind Mina, and really one of the great features behind the Mina project. And what they really solve this verification problem and produce a succinct blockchain that doesn't have this massive growth in size. And they do this by using zero-knowledge proofs. This is why we've been looking at them in the first half. And what they do is we use ZK SNARKs to compress the verification into a single proof. You can think of it like a certificate. So instead of if you receive a block on a blockchain, instead of having to verify the various parts are correct yourself, you would just look at this proof and you can very quickly verify the proof, this certificate, just to say, yes, this block is okay. So that's what the end users do. They just check this proof and they can see that is okay, rather than having to go through the entire transaction history in a block. And as we see, there's some recursion going on that gives us effectively a constant size blockchain. To go into that in a little bit more detail, we know that an updating a blockchain is really just a computation. We have a certain state of the blockchain at a particular time, and then we have some transition into a state at a later time when we add an extra block. And so what we're doing when we're verifying it really is verifying this transition between the blocks. And this is just a computation. And as I said earlier, ZK SNARKs, zero-knowledge proofs, are great at verifying computations and doing this efficiently. So we can do this, we can use our SNARK to verify the computation, the transition between the blocks. So if we have a correct initial state, we can verify that there's a transition to another state that must also be correct because the transition was correct. And so, yes, you only have to update, you only need to check the SNARK when you see the update to the chain. And the feature of SNARKs is that they are succinct and they are quick to check. Some links there for more details from the Mina paper and about the protocol. Perhaps one missing point that you do need to know about, that's great for verification, but what about the current state of the blockchain? And blockchains tend to look at state in two ways. There's the UTXO model of Bitcoin, where when we look at balances, we're looking back at all of the transactions that have led up to the current person having a particular balance, all of the unspent transactions that lead up to that point, and we're verifying by going back and checking that those all add up correctly, all match. And then there's the Ethereum version where they actually have accounts, and they keep the state of accounts. And so Mina does something similar. With there are nodes within the Mina system that do hold effectively the accounts of people, so you can hold the current state. And we also use Merkle proofs, so you can have a proof of your state within a Merkle tree of all of the accounts. But unlike Ethereum, we are just holding the current state here. We're not holding all of the intermediate states since the start of the blockchain. And that would be huge. Yeah, in Mina, we just hold the current state. And then consensus, this is quite different from, say, Ethereum. They have their own consensus mechanism, Ouroboros Genesis, which is a version of Ouroboros, which was I think that was the IIHK people who originally brought that out. It uses variable random functions, to choose who is going to be the producing blocks. And it is a proof of stake blockchain, so people are staking and then becoming block producers. But because of the VRF function, the VRF, this is included in the block, so this can be checked by people who are accepting the blocks. But all of this is contained and verified in a SNARK. So a resulting SNARK will say that transactions are signed by the correct person, by people who are allowed to spend from a particular account. The transactions are valid, so that the account has sufficient balance, for example, and that the consensus rules have been followed in producing the block. So we know our consensus has been followed. So we could effectively end up with one SNARK then that encapsulates all of this. And Mina does not just use one SNARK. I mean, there are SNARKs proving all the pieces in this verification, which are then pulled together into a resulting SNARK. And the design could have gone two ways. You could possibly, you could do this where each block would have its own SNARK, which would work, and you could just then pass these SNARKs around, so you would end up with one SNARK per block. But then our blockchain would carry on growing in size because of that, and so the verification would involve checking each one of these SNARKs going back to the Genesis block. So where Mina did a great breakthrough and really used technology very well is that they brought in the idea of recursive SNARKs. So what the Mina protocol does is to when it distributes a block, you'll have a SNARK, you'll have a proof of this, but the SNARK proves not just that the transition from the previous block to the current block was correct, and so that the current block is correct, but it also contains a proof that the previous block had a valid proof that proved that it was correct, and that previous block had a valid proof that the previous block to that was correct. So you have this recursion which goes all the way back to the starting block, the Genesis block. But because these are being built up into proofs, we don't need to check each of these proofs. They are all recursed and built up into the final proof, and the proof of the block that we're looking at the moment. Okay, so there are a number of roles or agents in the Mina system. So there will be some people who are producing blocks. These are similar to miners or stakers in other blockchains. They stake, and which guarantees their honesty, and they earn block rewards, similar way to Ethereum or Bitcoin. But that's all they really do. They're just block producers. Then in addition, we have SNARK producers, and they're the ones that are responsible for producing the proofs and for compressing all of this computation into something succinct which they then give to the block producers to distribute around the network. It's also possible that people will be professional block producers, so people may delegate their staking into staking pools as well. So those are the kind of the three actors I think that will be coming up in the Mina blockchain. Just to have a quick look at Pickles. So Pickles is the technology that is used for producing the ZK SNARKs on Mina. So it is the SNARK itself and all of the cryptography that goes into that. But it's also, they have a developer toolkit as well, which allows you to build on top of this. And if we compare Pickles to some of the other zero knowledge proofs, so if you look in that table, the proofs are in the different types of proofs are in the rows. So the first one in the row beneath Pickles, that is the common Stark. So it's same as Pickles. It's both. It is trustless. Halo produced, I think there was the Zcash team, and Pickles, I think, took a lot of technology from that team and from Halo, also trustless. Then the other types I've already mentioned, Plonk, used by Aztec, and Groth 16 is the kind of the breakthrough paper that led to ZK SNARKs and feasible implementations of zero knowledge proofs. But those last two, yeah, they require a trusted setup, which can be more or less feasible or flexible. And as we see, Pickles has a reasonable proof size, about 8 kilobytes. It's fast to produce the proof, and can easily do recursion, and it's open source, which is always a good thing. Some of the improvements in Pickles was they changed the field size, which led so some cryptographic improvements, which meant that their cryptographic functions or primitives sped up and reduced the overall size. So yeah, there's quite a recent improvement in Pickles. What can we do with our blockchain? Well, we can write snaps. So these are SNARK-powered applications, and these are designed to be the equivalent of dApps, really. So they're like dApps. They're applications that use a blockchain. They're decentralized, but they also have the features of privacy, because we're using zero knowledge proofs, and scalability, because of those properties. The way they work, effectively, unlike Ethereum, where you have repeated computation. So in an Ethereum smart contract, every node on the system that is running a virtual machine will be repeating computation, which is tremendously wasteful and tremendously inefficient, but it's there so that people can verify the correctness of the smart contract. The difference that Mina brings is that this computation that happens in the snap doesn't have to be repeated. So the computation can be done once by the developer, and then a SNARK can be produced that has the proof that this computation has been done correctly, and that can be then accepted by the people on the blockchain. So the workflow then is to create your snap. You can deploy this onto the Mina blockchain, the code itself, and then the developer themselves can call this to run this themselves. But this is not being run, as I say, multiple times, not being run by everybody. They can then compute the SNARK proof for this, and then pass this on to the other people in the Mina blockchain. Okay, and they have created kind of a standard snap to do the simple transaction of transferring tokens between accounts. So that's kind of a very basic one as a starting point. So let's just quickly look then at the Mina roadmap, where we are, where we're going. So, I mean, they started back in 2017. I think I first heard about them perhaps a little later than that, a couple of years ago, from the Zero Knowledge podcast. Very good podcast, by the way. Do recommend people to listen to it. But they had some people from Mina, or Coder as it was called back then, talking about this, and that's what really got me interested in the first place. I thought this idea of recursion was very, very smart, very clever way to solve some of the scalability problems. So they started back then. They've changed it quite a bit. I think they suddenly introduced new consensus mechanisms, so Ouroboros, and then Pickles was introduced even more recently. They've been running testnet, so we were involved with when the testnet was first launched, which I think was about a year ago, and then more recently there's been more phases of the testnet as we're heading towards the mainnet launch. So I think we're about to take part in the adversarial testnet. I think that's the next one that's coming up. So that's testnet 3.3. So we took part. We took part in this testnet. There were some problems, but we managed to get a node up and running and producing blocks, which was good. It's worth getting involved in this, getting involved in the testnet. Try running your own node. Try creating some transactions. There's incentives for people to get involved. They have a leaderboard, so when you do various things on the testnet, as you progress and do more and more on the testnet, you will be awarded points, and then they have a leaderboard that shows who's doing the most. They also have the Genesis program, and I'm really proud to say that we're involved in this. So this is the program that is going to be that's getting together the founding members that is going for the launch of the mainnet. They're looking for about 1,000 people to be involved, and they want this to be very distributed around the globe. So if you're they really are welcoming people from as many countries as possible. So if you're interested, please apply for that. And they have a grant of tokens to give to you for the program. The other way to get involved is via the testnet and to amass points on the leaderboard. And they have a very active Discord channel as well. So I really would encourage people to get involved. It's a very exciting technology. There's a lot going on. I mean, there's a lot happening in zero knowledge proofs generally, but Mina is at a really exciting point also. So there's plenty for people to get involved with. So I would really recommend you to have a look and get involved. As I say, we're really happy that we are involved. We're going to try in this meetup group to do more events, to talk more about, perhaps go into more detail about some of the aspects of Mina, and also give out updates to what's happening in the protocol, keep people updated. As as I say, I explained, I'm from this company XtraP at the beginning. We're very committed to community education, so we're very keen to keep this meetup going and to give out more resources and more information about Mina as it goes along. Okay, so that's I think we've been reasonable for time. Yeah, I've just got in time. That's all the slides I had. I'm sorry that it was a bit rushed. If you have questions, I'm happy to try and answer them now. If not, if you look at the slides, there are details there of how you can contact us and ask questions. So I'll be happy to answer questions later if you want to do that. Please put questions in chat if you have it, or just unmute yourself and ask the question.
So regarding the recording, I actually managed to start recording 2 minutes late, but the recording will be uploaded to YouTube channel, correct, Laurence?
Yep, definitely. Yeah, great. Thanks, Karen. Thanks for doing that. Thank you. Thank you. I'm glad you enjoyed it. Yes, we were running a testnet node. We're just waiting for the latest testnet the next testnet to come along. We'll run another node. Yeah, but well worth getting involved. Okay, so unless you have more questions, I'll finish there. Thank you so much for attending. It's nice to see people are interested in this area. Again, I would really recommend people to explore this more. The buzz around zero-knowledge proofs in general, and Mina in particular, I guess, now is very similar to the buzz I felt back, when Ethereum first came out. There's just so much happening, so much to get involved with, so much research to do. It's really a very exciting time. So I look forward to the next meetup, and we can talk more about where we're going and what the latest changes are. Thank you, everybody, for that. I'll leave it there. The slides are available. I'll just put the link to that. Actually, if I go back to the beginning, you get the link. There's the link to the slides if you want them. So yeah, thanks everyone to attending, and we'll hopefully get another meetup organized soon. Thank you.
One more question, Laurence.
Sure. Yeah.
So the ZKPs are hot, yes, but is there a chance for Mina to succeed, or will there be only zero-knowledge proofs on Ethereum and solutions on Ethereum? Because what chances does Mina have to get enough users and liquidity to succeed?
Yeah, fair point. So I think that the real difference, Ethereum are also using zero-knowledge proofs. So they're things like roll-ups. So they try to use them. The difference, I guess, is that Mina is always going to be succinct. So you've got this constant size blockchain. That whereas Ethereum, it is always going to be growing. I mean, even though they're solving some of the scalability, maybe the throughput by using zero-knowledge proofs, the size of the chain is always going to be increasing. Whereas Mina has this advantage that it is, because of their clever recursion, they're going to have a constant size blockchain. As to whether they'll get enough people to succeed, I don't know. I hope so. It's a good point. They perhaps in one of the next sessions we can have a look at some of the economics behind it as well. They have an economic white paper on their site, so we can perhaps go through that. Maybe that will shed some light on it.
Yeah, I think what's worth mentioning is that Mina is really focused into building the community. And for example, the Genesis program is one of the ways that will actually allow the first block producers and the first members to be active straight from the mainnet launch. So in that way, us, for example, will be running the mainnet node, and that will already give some, possibility and decentralization in the way of who's running the node. Mina is really into building the community, and also I just hope as well that it will go well.
Yeah.
Thank you.
Great. Thanks, Fox. Thanks, everybody. We'll finish here then. Thanks again for attending. Please look at the meetup site. We'll get more details of our next meetup there, and we'll put links to the presentations and everything there, and the YouTube video as well. Thanks, everyone. Have a good evening. We'll see you later.
Cheers. Thank you, everyone. Bye.